Alright, so in class we've already done an introduction into what linear approximation looks like, and so this video is just going to show you how to approach the typical problems you come across. So let's remember first what our equation is that we've been working with for a while, which is our point-slope form. And basically, if we're looking at a specific point, A, f of A, and we're trying to approximate it using this tangent line equation, we can plug in f of A for the y value. The slope at a given point we write as the derivative at that x value, and then times x minus that specific x value we're looking at. And then all we do at that point is we simply solve for y, the estimated y value. And so we get this equation that looks something like this. And sometimes people put the f of A first. It doesn't matter. I tend to put mine in this particular setup just because it's more of a habit. But you could put the f of A portion at the front if you prefer that. And so with linearization, we specifically use the notation that to estimate a function at a given value, and you have to use little estimation signs. We use a capital L for linearization often, and then the rest like you see above. Okay, so this is what we're going to be using for our two example problems. Alright, so in doing these examples, they could ask you for the linearization of a function, the linear approximation, the tangent line approximation. There's lots of ways you might be asked to do this particular skill. Our first example is pretty basic, and we're going to start with a more real-world type. Let's say you're cooking a turkey and you're checking the temperature at various times. So after you stuff the turkey, it's 50 degrees Fahrenheit, and you put it into the oven at 325 degrees Fahrenheit. After 1 hour, the thermometer reads 93 degrees, and after a second hour, it reads 129. Predict the turkey's temperature after 3 hours. So in a problem like this one, we don't have an equation to work with. So usually they just give you reference points. And in this case, we have 3. So we have the temperature at the beginning, which was not 325. That was the oven. If the turkey were that hot, I don't think we would need an oven. All right, so 50. After 1 hour, it would be at 93. 2 hours, it would be 129. And now we're estimating the third hour. And since we don't have an equation to use, we're going to just use the values closest to it. Sorry, Stella got really excited there. So the time at 2 hours is the point I'm going to use. So I'm going to use the coordinate point 2, 129 as our point. And then I'm going to estimate the slope at 2. So whatever x value you use for the point, that's where you estimate the slope as well. And we're going to have to do the average rate of change here. Now you could choose 0 or 1 as your other point. I'm just going to go with 1 because it's closer, but technically either would be fine. So it's going to be change in y over change in x, and that's going to give us approximately 36 as the slope. So then to find or estimate the temperature, we're going to have, actually let's just do the generic linearization first. So our linearization would look like the slope times x minus our point x value plus our y value at our point. And therefore, if we were to estimate the temperature of the turkey after 3 hours, let's see, that would be L of 3, which is going to give us 36 times 3 minus 2 plus 129, and of course 3 minus 2 is just 1, so we essentially get 36 plus 129, and it estimates to 165 degrees Fahrenheit, which is so exciting. So that's how we would go about this without a formula to work with and just using either table values or coordinate points given to us. Another common question you get is when it asks you if your estimation is an over or under estimate. And sometimes we are able to use the second derivative for this, but in this case, since we don't have a function to find the second derivative, we're just going to have to think about the coordinate points graphically. So I'm just going to make a very quick scale here of the temperature and what it looks like it's doing. So we know initially it was at 50, then it went up to 93, and then it went up to 129, something in this general shape. Okay, and we know as far as temperature goes, it's just going to reach whatever the oven's set to. So it's going to kind of flatten out eventually. But you can see there's a slight curve here, and this would make what we call concave down. So if we were to estimate a line at 3 using 2 as our point of tangency, you can see that that tangent line at 3 would be falling above the curve itself. So in this particular case, we would say that our estimation would be an overestimate. So we'll say 165 degrees Fahrenheit is an overestimate because the tangent line is above the curve. Okay, and this is always going to be the case whenever we have a function that is concave down. So that's another thing you can say instead as an explanation, is you can just say, since it's concave down, we know it's going to be an overestimate based on our model. Okay, so here's the second example, which is one where we're actually given an equation. And just to clarify, this is like a square root function here. I couldn't get the fancy notation to work for me in Google Slides, so but that's what's really going on there. So we're going to find the linearization of the function square root of x plus 3 at x equals 1 and use it to approximate 3.98 and 4.05, and then determine if they're over or under estimates. So let's go ahead and start. A lot of times I just like to write the function and make sure it's ready for me to take the derivative easily. So in this case, I would rewrite it as x plus 3 to the 1/2. And then I would go ahead and figure out the coordinate point I'm working with, which again, in this case, they're giving me x equals 1. So I'm going to find f of 1 so that I'm able to find the y coordinate that goes with it. So that would be the square root of 1 plus 3, which would be square root 4, which would simply be 2. So we're working with the point 1, 2. And now that I have the point, I need the slope. So that means I need to take the derivative. So then I'm going to take the derivative. Okay, so 1/2 times x plus 3 to the negative 1/2. And don't forget the chain rule. In this case, our chain rule would just be 1. And once I have the derivative, and I write it in an easier way to evaluate, so that would be 2 square root of x plus 3. Then I can come over here and actually find the slope at the point we're using, which is 1, which is nice and easy. Okay, so that's going to give me 1 over 2 root 4, which is just 1 over 2 times 2, which is 1/4. So now we have a slope of 1/4. Okay, so we've got our point, we've got our slope, which means we can write our linear approximation model. So in this case, we're going to say that L of x equals our slope times x minus 1 plus 2. Okay, and now we're actually going to use this to estimate the 2 that they're asking about. So actually the part that I think can sometimes be the most difficult with linearization is figuring out when they give me an x value how it is connected to what we're plugging in and the function. So for instance, if we're trying to estimate the square root of 3.98, we're using the function x plus 3. So what really is our x value? Our x value is not 3.98. It's whatever I added to 3 to get 3.98, which in this case means I'm really using an x value of 0.98. And that's the step that a lot of people get a little turned around on. So again, you're trying to figure out if this is what I'm seeing evaluated, what was the actual x I was using there. And then from there, it's pretty straightforward. So we can say that f of 0.98 estimates to L of 0.98, which is 1/4 times 0.98 minus 1 plus 2. And that's just a matter of simplifying it. And if you do your calculations correctly, you're going to get something close to 1.995. Okay. And that's it. So now let's do the same thing for 4.05. Okay, so again, I kind of go through this process for each one of these types of problems. So I'm trying to find the square root of 4.05. And my function is, again, x plus 3. Then what was it that I added to 3 to get 4.05? And often it's going to be obviously close to the x value our model's based on. Otherwise, it's not a good model. So the first one was a little under 1. This one is a little over 1. And it's when x is 1.05. Okay, so f of 1.05 estimates to L of 1.05, which is 1/4 times, not x, I get going sometimes, 1.05 minus 1 plus 2. And again, we'll just simply evaluate all of this, and then we will get our linearization model estimate, which in this case comes out to be 2.0125. All right, so the last thing we're going to do on this one is answer that ever popular question of if it's an overestimate or underestimate. And to do this, we're going to have to find the second derivative. So just as a reminder, we already found the first derivative, which was 1/2 times x plus 3 to the negative 1/2. And so now I'm simply going to find the second derivative, which would become negative 1/4 times x plus 3 to the negative 3/2. And remember, this negative simply means we end up with a denominator. So if I'm plugging in an x equals 1 into this equation, that's what I'm going to use to determine if I get a positive or negative derivative. But I can already see, because of our negative coefficient, that we will end up with a negative value. But let's kind of go through the motions for our first example. So we would just plug in the x value we're looking at of 1 plus 3 to the negative 3/2, which is pretty ugly to do in this form. So I'm actually going to turn it back into a fraction. So we would have 4/, let's see, the square root of 4, which is what, 2? So times 2 cubed. Okay, which gives me -1 over, again, some sort of positive number. You don't really have to find the exact value. 4 times 8. Okay, and so we'll be able to say that this means that the function is concave down, which means that any sort of tangent line estimation is going to be an overestimate. So we'll say both are overestimates since f double prime of x is negative, and thus f of x is concave down. So anytime a function is concave down, we have an overestimate. Anytime a function is concave up, we have an underestimate. And just to clarify, the function doesn't actually look like a parabola. I mean, you can also just think about visually, we know square root function kind of is this type of concave down. So again, any sort of tangent line we draw would create an overestimation of some type. So you can either think of it visually or use your second derivative to verify whether a function is concave up or down. And this will conclude our video notes on linearization.